School of Management Studies IGNOU presents an audiobook on the course MMPC 005 Quantitative Analysis for Managerial Applications for MBA program. Block 3 Sampling and Sampling Distributions. Unit 10 Sampling Distributions.
After completing this unit, you should be able to understand the meaning of sampling distribution of a sample statistic, obtain the sampling distribution of the mean, get an understanding of the sampling distribution of variance, construct the sampling distribution of the proportion, know the central limit theorem and appreciate why it is used so extensively in practice, develop confidence intervals for the population mean and the population proportion, and determine the sample size required while estimating the population mean or the population proportion. Introduction. Having discussed the various methods available for picking up a sample from a population, we would naturally be interested in drawing inferences about the population based on our observations made on the sample members. This could mean estimating the value of a population parameter, testing a statistical hypothesis about the population, comparing two or more populations, performing correlation and regression analysis on more than one variable measured on the sample members, and many other inferences. We shall discuss some of these problems in this and subsequent units. What is a sampling distribution? Suppose we are interested in drawing some inference regarding the weight of containers produced by an automatic filling machine. Our population therefore consists of all the filled containers produced in the past as well as those which are going to be produced in the future by the automatic filling machine. We pick up a sample of size n and take measurements regarding the characteristic we are interested in, viz. The weight of the filled container on each of our sample members. We thus end up with n sample values, that is x1, x2 till xn. As described in the previous unit, any quantity which can be determined as a function of the sample values x1, x2 till xn is called a sample statistic. Referring to our earlier discussion on the concept of a random variable, it is not difficult to see that any sample statistic is a random variable and therefore has a probability distribution or a probability density function. It is also known as the sampling distribution of the statistic. In practice, we refer to the sampling distributions of only the commonly used sampling statistics like the sample mean, sample variance, sample proportion, sample median, etc., which have a role in making inferences about the population. Why study sampling distributions? Sample statistics form the basis of all inferences drawn about populations. If we know the probability distribution of the sample statistic, then we can calculate the probability that the sample statistic assumes a particular value if it is a discrete random variable or has a value in a given interval. This ability to calculate the probability that the sample statistic lies in a particular interval is the most important factor in all statistical inferences. We will demonstrate this by an example. Suppose we know that 45% of the population of all users of talcum powder prefer our brand to the next competing brand. A new improved version of our brand has been developed and given to a random sample of 100 talcum powder users for use. If 60 of these prefer our new improved version to the next competing brand, what should we conclude? For an answer, we would like to know the probability that the sample proportion in a sample of size 100 is as large as 60% or higher when the true population proportion is only 45%. That is, assuming that the new version is no better than the old. If this probability is quite large, say 0.5, we might conclude that the high sample proportion which 60% is perhaps because of sampling errors, and the new version is not really superior to the old. On the other hand, if this probability works out to a very small figure, say 0.001, then rather than concluding that, we might conclude that the true population proportion is higher than 45%, that is, the new version is actually superior to the old one as perceived by members of the population. To calculate this probability, we need to know the probability distribution of sample proportion or the sampling distribution of the proportion. Sampling distribution of the mean. We shall first discuss the sampling distribution of the mean. We start by discussing the concept of the sample mean and then study its expected value and variance in the general case. We shall end this section by describing the sampling distribution of the mean in the special case when the population distribution is normal. The sample mean. Suppose we have a simple random sample of size n picked up from a population. We take measurements on each sample member in the characteristic of our interest and denote the observation as x1, x2 till xn respectively. The sample mean for this sample represented by x is defined as mean is equal to x1 plus x2 plus x3 till plus xn over n. If we pick up another sample of size n from the same population, we might end up with a totally different set of sample values and so a different sample mean. Therefore, there are many, perhaps infinite possible values of the sample mean, and the particular value that we obtain if we pick up only one sample is determined only by chance causes. The distribution of the sample mean is also referred to as the sampling distribution of the mean. However, to observe the distribution of mean empirically, we have to take many samples of size n and determine the value of mean for each sample. Then, looking at the various observed values of z, it might be possible to get an idea of the nature of the distribution. Sampling from infinite populations. We shall study the distribution of z in two cases. One, when the population is finite and we are sampling without replacement, and the other, when the population is infinitely large or when the sampling is done with replacement. We have arrived at two very important results for the case when the population is infinitely large, which we shall be using very often. The first says that the expected value of the sample mean is the same as the population mean, while the second says that the variance of the sample mean is the variance of the population divided by the sample size. If we take a large number of samples of size n, then the average value of the sample means tends to be close to the true population mean. On the other hand, if the sample size is increased, then the variance gets reduced, and by selecting an appropriately large value of n, the variance of x can be made as small as desired. The standard deviation of x is also called the standard error of the mean. Very often we estimate the population mean by the sample mean. The standard error of the mean indicates the extent to which the observed value of sample mean can be taken away from the true value due to sampling errors. For example, if the standard error of the mean is small, we are reasonably confident that whatever sample mean value we have observed cannot be very far away from the true value. Sampling with replacement. These results have been obtained under the assumption that the random variables x1, x2 till xn are independent. This assumption is valid when the population is infinitely large. It is also valid when the sampling is done with replacement so that the population is back to the same form before the next sample member is picked up. Sampling without replacement from finite populations. When a sample is picked up without replacement from a finite population, the probability distribution of the second random variable depends on what has been the outcome of the first pick and so on. As the n random variables representing the n sample members do not remain independent, the expression for the variance of x changes. In practice, almost all the samples used picked up without replacement. Also, most populations are finite, although they may be very large, and so the standard error of the mean should theoretically be found by using the expression given here. However, if the population size n is large and consequently the sampling ratio of small n over capital N small, then the finite population multiplier is close to 1 and is not used, thus treating large finite populations as if they were infinitely large. Sampling from normal populations. We have understood earlier that the normal distribution occurs very frequently among many natural phenomena. For example, heights or weights of individuals, the weights of filled cans from an automatic machine, the hardness obtained by heat treatment, etc. are distributed normally. We also know that the sum of two independent random variables will follow a normal distribution if each of the two random variables belongs to a normal population. The sample mean, as we have understood earlier, is the sum of n random variables x1, x2 till xn, each divided by n. Now, if each of these random variables is from the same normal population, it is not difficult to see that x would also be distributed normally. Central limit theorem. If x1, x2 till xn are n random variables which are independent and having the same distribution with mean and standard deviation, then if n is infinity, the limiting distribution of the standardized mean is the standard normal distribution. In practice, if the sample size is sufficiently large, we need not know the population distribution because the central limit theorem assures us that the distribution of x can be approximated by a normal distribution. A sample size larger than 30 is generally considered to be large enough for this purpose. Many practical samples are of size higher than 30. In all these cases, we know that the sampling distribution of the mean can be approximated by a normal distribution with an expected value equal to the population mean and a variance which is equal to the population variance divided by the sample size n. We need to use the central limit theorem when the population distribution is either unknown or known to be non-normal. If the population distribution is known to be normal, then will also be distributed normally irrespective of the sample size. Sampling distribution of the variance. We shall now discuss the sampling distribution of the variance. We shall first introduce the concept of sample variance and then present the chi-square distribution, which helps us in working out probabilities for the sample variance when the population is distributed normally. The sample variance. By now, it is implicitly clear that we use the sample mean to estimate the population mean when that parameter is unknown. Similarly, we use a sample statistic called the sample variance to estimate the population variance. The sample variance is usually denoted by S square and it again captures some kind of an average of the square of deviations of the sample values from the sample mean. The deviations are measured from the sample mean and not from the population mean, and secondly, the sum of square deviations is divided by n minus 1 and not by n. Consequently, we can calculate the sample variance based only on the sample values without knowing the value of any population parameter. The chi-square distribution. If the random variable x has the standard normal distribution, what would be the distribution of x square? Intuitively speaking, it would be quite different from a normal distribution because now x square, being a squared term, can assume only non-negative values. The probability density of x square will be the highest near 0 because most of the x value are close to 0 in a standard normal distribution. This distribution is called the chi-square distribution with 1 degree of freedom. The chi-square distribution has only one parameter with the degrees of freedom, and so there are many chi-square distributions, each with its own degrees of freedom. In statistical tables, chi-square values for different areas under the right tail and the left tail of various chi-square distributions are tabulated. If x1, x2 till xn are independent random variables, each having a standard normal distribution, then x square 1 plus x square 2 plus till x square n will have a chi-square distribution with n degrees of freedom. If y1 and y2 are independent random variables having chi-square distributions with y1 and y2 degrees of freedom, then y plus 1 y2 will have a chi-square distribution with y1 plus y2 degrees of freedom. If y1 and y2 are independent random variables such that y1 has a chi-square distribution with y1 degrees of freedom and y1 plus y2 has a chi-square distribution with y more than y1 degrees of freedom, then y2 will have a chi-square distribution with y minus y1 degrees of freedom. Expected value and variance of s square. The mean of a chi-square distribution is equal to its degrees of freedom and the variance is equal to twice the degrees of freedom. This can be used to find the expected value and the variance of s square. If we take a large number of samples, each with a sample size of n, from a normal population with mean and variance, each sample will perhaps have a different value for its sample variance. But the average of a large number of values of sample variance will be close to variance. Also, the variance of s square falls as the sample size increases. If the population does not have a normal distribution, then nothing can be said about the distribution of s square. The student's distribution. In actual practice, the value of the population standard deviation is often unknown, which makes it necessary to replace this with an estimate, usually by S, the sample standard deviation. In such cases, we would like to know the exact sampling distribution for random samples from normal populations, and this is provided by the t distribution, which is also known as the student's t distribution after the pen name adopted by its author. The concept of the t statistic. If x is a random variable having the standard normal distribution and y is a random variable having a chi-square distribution with v degrees of freedom, and if x and y are independent, then the random variable t, which is equal to x over square root of y by v, has a distribution called the t distribution or the student's t distribution with v degrees of freedom. There are many t distributions, each with its degrees of freedom, which is the only parameter of this distribution. A t distribution is similar to the standard normal distribution, only it is flatter and wider, thus having longer tails. As the degrees of freedom increase, the t distribution comes closer to the standard normal distribution, and when the degrees of freedom become infinitely large, the t distribution and the z distribution become indistinguishable. The t distribution in practice. If we have a random sample of size n from a normal population with mean and variance, then we know that the sample mean will be distributed normally with mean and variance. We also know that such a situation will have a chi-square distribution with n-1 degrees of freedom. If the sample size n is large, the t distribution with large degrees of freedom can be approximated by the z distribution. The t distribution is used when the degrees of freedom are not larger than 30. If the degrees of freedom are larger than 30, the t distribution is approximated by the standard normal or the z distribution. The t distribution is again extensively tabulated because it is used quite frequently. As it is a symmetrical distribution, only one tail is generally tabulated and the other tail values can be worked out by using the property of symmetry. Sampling distribution of the proportion. Suppose we know that a proportion P of the population possesses a particular attribute that is of interest to use. For example, a proportion P of the population prefer our product to the next competing brand. This also implies that a proportion 1 minus P of the population do not prefer our product as compared to the next competing brand. If we pick up one member of the population at random, the probability of success, that is the probability that this person will prefer our product to the next competing brand, is P. If the population is large enough, then even if we make repeated trials which are considered to be independent, each with the probability of success equal to P, in such a case, if we make n repeated trials to pick up a sample size of n, the probability of X success in the sample is given by a binomial probability distribution. Interval estimation. Suppose we want to estimate the mean income of a population of households residing in a part of a city. We might proceed by picking up a random sample of 100 households from the population and calculate the sample mean, that is the mean income of the 100 sample households. In the absence of any other information, the sample mean can be used as a point of estimate of the population mean. However, if we also want to convey the precision involved in this estimation, we need distributions to give the standard error of the mean. The standard error of the mean depends on the population variance and the sample size. The lower the standard error of the mean, the greater is the confidence on the correctness of our estimation. This process is further refined in interval estimation, wherein we present our estimate as an interval and quantify our confidence so that the true population parameter is contained by the estimated interval. The confidence level. As mentioned earlier, the sample mean is our estimate of the population mean. If we are asked to give an interval as our estimate, then we would add a range on the upper and the lower side of the sample mean and give that interval as our estimate. The larger the interval, the greater is our confidence that the interval does contain the true population mean. It is to be noted that the true population mean is a constant and is not a variable. On the other hand, the interval that we specify is a random interval whose position depends on the sample mean. For example, if the sample mean is 50 and the standard error of the mean is 5, we may specify our interval estimate as 45 or 55, that is from 45 and 55, that is from 45 to 55, which spans one standard error of the mean on either side of the sample mean. On the other hand, if the interval estimate is specified as 40 and 60, that is spanning two standard errors of the mean on either side of the sample mean, we are more confident that the latter interval contains the true population mean as compared to the former. However, if the confidence level is raised too high, the corresponding interval may become too wide to be of any practical use. The confidence level therefore may be defined as the probability that the interval estimate will contain the true value of the population parameter that is being estimated. If we say that a 95% confidence interval for the population mean is obtained by spanning 1.96 times the standard error of the mean on either side of the sample mean, we mean that we take a large number of samples of size n, say 1000, and obtain the interval estimates from each of these 1000 samples, and then 95% of these interval estimates would contain the true population mean. Sample size for estimating population mean. We assume that the population distribution is normal and the population standard deviation is known. In such a case, the sample size required for a given confidence level and a required accuracy can be easily determined. Now let's summarize the unit. We have introduced the concept of sampling distributions in this unit. We have discussed the sampling distributions of some commonly used statistics and also made you understand some applications of the same. A sampling distribution of a sample statistic has been introduced as the probability distribution or the probability density function of the sample statistic. In the sampling distribution of the mean, we find that if the population distribution is normal, the sample mean is also distributed normally with the same mean, but with a smaller standard deviation. In fact, the standard deviation of the sample mean, also known as the standard error of the mean, is found to be equal to the population standard deviation divided by the sample size. We have also presented a very important result called the central limit theorem, which assures us that if the sample size is large enough or greater than 30, the sampling distribution of the mean could be approximated by corresponding normal distribution and standard deviation. We have then explored the sampling distribution of the variance and found that a related quantity would have a chi-square distribution with n-1 degrees of freedom. We have learned that the chi-square distribution is tabulated extensively, and so any probability calculations regarding S square could be easily made by referring to the tables for the chi-square distribution. We have introduced one more distribution, viz. The T distribution, which is found to be applicable when the sampling distribution of the mean is of interest, but the population standard deviation is unknown. It is noticed that if the sample size is large enough, that is n is greater than 30, the T distribution is actually very close to the standard normal distribution. Students, you can refer to your self-learning material for studying the sampling distribution of the proportion and also two applications of the sampling distributions. One is in developing an interval estimate for a population parameter with a given confidence level, which is conceptualized as the probability that a random interval will contain the true value of the parameter. The second application is to determine the sample size required while estimating the population mean or the population proportion.
We were listening to the audiobook by the School of Management Studies IGNOU for MBA program, course code MMPC 005, Quantitative Analysis for Managerial Applications. Course Coordinator, Professor Anurag Saxena, School of Management Studies IGNOU. Voiceover by Harpreet Kaur. Edited by Uday Sharma. Program assisted by Tarannum Jahan and Jagbandhu Jana. Program produced by Dr. Manoj Kumar Singh. This program was brought to you by Electronic Media Production Center of Indira Gandhi National Open University.